Integrals. Integration. The functions that could possibly have given function as a derivative are called antiderivatives or primitive of the function. The formula that gives all these antiderivatives is called the indefinite integral of the function, and such process of finding antiderivatives is called integration. The development of integral calculus arises out of the efforts of solving the problems of the following types. A. The problem of finding a function whenever its derivative is given. B. The problem of finding the area bounded by the graph of a function under certain conditions. These two problems lead to the forms of the integrals. Example, indefinite and definite integrals, which together constitute the integral calculus. Integration as an inverse process of differentiation. Instead of differentiating a function, we are given derivative of a function and asked to find its primitive, that is, the original function. Such a process is called integration or antidifferentiation.
Number 1. d by dx into sin x is equal to cos x. Number 2. d by dx into x cube by 3 is equal to x square. And number 3. d by dx into e power x is equal to e power x. In one, the function cos x is the derived function of sin x. We say that sin x is an antiderivative or an integral of cos x. Similarly, in 2 and 3, x cube by 3 and e power x are the antiderivatives or integrals of x square and e power x respectively. Again, we note that for any real number c treated as constant function, its derivative is 0 and hence we can write 1, 2 and 3 as follows. C is customarily referred to as arbitrary constant. In fact, C is the parameter by varying which one gets different antiderivatives or integrals of the given function. More generally, if there is a function f such that d by dx into f of x is equal to f of x if for all x belongs to I, then for any arbitrary real number c, also called constant of integration, d by dx into f of x plus c is equal to f of x where x belongs to I. Thus, f plus c, c belongs to R denotes a family of antiderivatives of f.
Table. Symbols, terms, phrases, and meanings are shown in the table.
Geometrical interpretation of indefinite integrals. Let f of x is equal to 2x. Then, integral f of x into dx is equal to x square plus c. For different values of c, we get different integrals. Y is equal to x square plus c, where c is arbitrary constant represents a family of integrals. For c is equal to 0, we obtain y is equal to x square, a parabola with its vertex on the origin. The curve y is equal to x square plus 1 for c is equal to 1 is obtained by shifting the parabola y is equal to x square 1 unit along y-axis in positive direction. For c is equal to minus 1, y is equal to x square minus 1 is obtained by shifting the parabola y is equal to x square 1 unit along y-axis in the negative direction. Thus, for each positive value of c, each parabola of the family has its vertex on the positive side of the y-axis, and for negative values of c, each has its vertex along the negative side of the y-axis. Let us consider the intersection of all these parabolas by a line x is equal to a. In the figure, we have taken a greater than 0. The same is true when a is lesser than 0. If the line x is equal to a intersects the parabolas y is equal to x square, y is equal to x square plus 1, y is equal to x square plus 2, y is equal to x square minus 1, y is equal to x square minus 2 at p0, p1, p2, p minus 1, p minus 2, etc. respectively. Then dy by dx at these points equals to a. This indicates that the tangents to the curves at these points are parallel. Thus, integral 2x into dx is equal to x square plus c is equal to fc of x into c implies that the tangents to all the curves y is equal to fc of x, c belongs to R at the points of intersection of the curves by the line x is equal to a belongs to R or parallel. Further, the following equation statement integral f of x into dx is equal to f of x plus c is equal to y represents a family of curves. The different values of c will correspond any one of the curves parallel to itself. This is the geometrical interpretation of indefinite integral.
Indefinite integral properties. The process of differentiation and integration are inverses of each other. D by dx integral f of x dx is equal to f of x, and integral f dash of x dx is equal to f of x plus c, where c is any arbitrary constant. The proof is shown on the screen. Two indefinite integrals with the same derivative lead to the same family of curves, and so they are equivalent. The proof is shown on the screen.
Write an antiderivative for each of the following functions using the method of inspection 1 by x where x is not equal to 0. Solution. We know that d by dx into log x is equal to 1 by x where x is greater than 0 and d by dx into log of minus x is equal to 1 by minus x into minus 1 is equal to 1 by x, where x is lesser than 0. Combining above, we get d by dx into log of modulus x is equal to 1 by x, where x is not equal to 0. Therefore, integral 1 by x into dx is equal to log of modulus x is one of the antiderivatives of 1 by x.
Example, find the following integrals. Integral x cube minus 1 by x square dx. Solution, we have integral x cube minus 1 by x square dx equal to integral x dx minus integral x minus 2 dx by property V. Integral x cube by x square dx minus integral 1 by x square dx equal to integral x dx minus integral x minus 2 dx implies integral x dx equal to x power n plus 1 by n plus 1 plus c equal to x power 1 plus 1 by 1 plus 1 plus c1 minus x power minus 2 plus 1 by minus 2 plus 1 plus c2. C1, C2 are constants of integration equal to x square by 2 plus C1 minus x power minus 1 by minus 1 minus C2 equal to x square by 2 plus 1 by x plus C1 minus C2 equal to x square by 2 plus 1 by x plus c, where c equal to C1 minus C2 is another constant of integration. Example, find the antiderivative f of f defined by f of x equal to 4x cube minus 6, where f of 0 equal to 3. Solution, one antiderivative of f of x is equal to x power 4 minus 6x, since d by dx x power 4 minus 6x equal to 4x cube minus 6 equal to 4x power 4 minus 1 minus 6x power 1 minus 1. Therefore, the antiderivative f is given by f of x equal to x power 4 minus 6x plus c, where c is constant. Given that f of 0 equal to 3, which gives put x equal to 3. 3 equal to 0 minus 6 into 0 plus c, or c equal to 3. Hence, the required antiderivative is the unique function f defined by f of x equal to x power 4 minus 6x plus 3.
Comparison between differentiation and integration are given on the screen. Methods of integration. Methods for finding the integrals by reducing them into standard forms are: 1. Integration by substitution, 2. Integration using partial fractions, and 3. Integration by parts.
Integration by substitution. The given integral f of x into dx, can be transformed into another form y, changing the independent variable x to t by substituting x is equal to g of t. Consider I is equal to integral f of x into dx. Put x is equal to g of t, so that dx by dt is equal to g dash of t. We write dx is equal to g dash of t into dt. Thus, I is equal to integral f of x into dx is equal to integral f of g into t the whole into g dash of t into dt.
Some important integrals involving trigonometric functions.
integral 1 by 1 plus tan x into dx. Solution. Integral dx by 1 plus tan x is equal to integral cos x into dx by cos x plus sin x is equal to 1 by 2 into integral cos x plus sin x plus cos x minus sin x into dx by cos x plus sin x is equal to 1 by 2 into integral dx plus 1 by 2 into integral cos x minus sin x by cos x plus sin x into dx is equal to x by 2 plus c1 by 2 plus 1 by 2 into integral cos x minus sin x by cos x plus sin x into dx. Now, consider I is equal to integral cos x minus sin x by cos x plus sin x into dx. Put cos x plus sin x is equal to t, so that cos x minus sin x into dx is equal to dt. Therefore, I is equal to integral dt by t is equal to log modulus of t plus c2 is equal to log modulus of cos x plus sin x plus c2. Putting it in 1, we get integral dx by 1 plus tan x is equal to x by 2 plus c1 by 2 plus 1 by 2 into log of modulus cos x plus sin x plus c2 by 2 is equal to x by 2 plus 1 by 2 into log into modulus of cos x plus sin x plus c1 by 2 plus c2 by 2 is equal to x by 2 plus 1 by 2 into log modulus of cos x plus sin x plus c, where c is equal to c1 by 2 plus c2 by 2.
Integration. Trigonometric identities. When the integrand involves some trigonometric functions, we use some known identities to find the integral.
Find integral cos square x into dx. Integral sin cube x into dx. Solution. Subdivision 1. Recall the identity cos 2x is equal to 2 cos square x minus 1, which gives cos square x is equal to 1 plus cos 2x by 2. Therefore, integral cos square x into dx is equal to 1 by 2 into integral 1 plus cos 2x into dx is equal to 1 by 2 into integral dx plus 1 by 2 into integral cos 2x dx is equal to x by 2 plus 1 by 4 into sin 2x plus c. Subdivision 2. From the identity sin 3x is equal to 3 sin x minus 4 sin cube x, we find that sin cube x is equal to 3 sin x minus sin 3x by 4. Therefore, integral sin cube x dx is equal to 3 by 4 into integral sin x dx minus 1 by 4 into integral sin 3x into dx is equal to minus 3 by 4 into cos x plus 1 by 12 into cos 3x plus c. Find the following integrals. Integral dx by the square root of 2x minus x square. Solution. Integral dx by the square root of 2x minus x square is equal to integral dx by the square root of 1 minus x minus 1 to the whole square. Put x minus 1 is equal to t. Then dx is equal to dt. Therefore, integral dx by the square root of 2x minus x square is equal to integral dt by the square root of 1 minus t square is equal to sin inverse of t plus c is equal to sin inverse of x minus 1 plus c.
Integration by partial fractions. A rational function is defined as the ratio of two polynomials in the form of p of x by q of x, where p of x and q of x are polynomials in x and q of x not equal to 0. If the degree of p of x is less than the degree of q of x, then the rational function is called proper. Otherwise, it is called improper. The improper rational functions can be reduced to the proper rational function by long division process. Thus, if p of x by q of x is improper, then p of x by q of x is equal to t of x plus p1 of x by q of x, where t of x is a polynomial in x and p1 of x by q of x is a proper rational function.
Integration by partial fractions. The following table indicates the type of simpler partial fractions that are to be associated with various kinds of rational functions.
Find integral dx by x plus 1 into x plus 2. Solution. The integrand is a proper rational function. Therefore, by using the form of partial fraction, we write 1 by x plus 1 into x plus 2 is equal to a by x plus 1 plus b by x plus 2, where real numbers a and b are to be determined suitably. This gives 1 is equal to a into x plus 2 plus b into x plus 1. Equating the coefficients of x and the constant term, we get a plus b is equal to 0 and 2a plus b is equal to 1. Solving these equations, we get a is equal to 1 and b is equal to minus 1. Thus, the integrand is given by 1 by x plus 1 into x plus 2 is equal to 1 by x plus 1 plus minus 1 by x plus 2. Therefore, integral dx by x plus 1 into x plus 2 is equal to integral dx by x plus 1 minus integral dx by x plus 2 is equal to log of modulus x plus 1 minus log of modulus x plus 2 plus c is equal to log of modulus x plus 1 by x plus 2 plus c. Find integral x cos x into dx. Solution. Put f of x is equal to x. First function. G of x is equal to cos x. Second function. Then integration by parts gives integral x cos x dx is equal to x into integral cos x dx minus integral d by dx into x into integral cos x dx into dx is equal to x sin x minus integral sin x into dx is equal to x sin x plus cos x plus c. Suppose we take f of x is equal to cos x and g of x is equal to x. Then integral x cos x dx is equal to cos x into integral x dx minus integral d by dx into cos x into integral x dx into dx is equal to cos x into x square by 2 plus integral sin x into x square by 2 into dx. Observe that while finding the integral of the second function, we did not add any constant of integration. If we write the integral of the second function cos x as sin x plus k, where k is any constant, Then integral x cos x dx is equal to x into sin x plus k minus integral sin x plus k into dx is equal to x into sin x plus k minus integral sin x into dx minus integral k dx is equal to x into sin x plus k minus cos x minus kx plus c is equal to x sin x plus cos x plus c.
Example, find integral e power x sin x dx. Solution, take e power x as the first function and sin x as the second function. Then, integrating by parts, we have I equal to integral e power x sin x dx equal to e power x minus cos x plus integral e power x cos x dx equal to minus e power x cos x plus I1 say. Taking e power x and cos x as the first and second functions respectively in I1, we get I1 equal to e power x sin x minus integral e power x sin x dx. Substituting the value of I1 in 1, we get I1 equal to minus e power x cos x plus e power x sin x minus 1 or 2 I equal to e power x into sin x minus cos x. Hence, I equal to integral e power x sin x dx equal to e power x by 2 sin x minus cos x plus c. Example, find integral e power x tan minus 1x plus 1 by 1 plus x square dx. Solution, we have I equal to integral e power x tan power minus 1x plus 1 by 1 plus x square dx. Consider f of x equal to tan minus 1x, then f dash x equal to 1 by 1 plus x square. Thus, the given integrated is of the form e power x f of x plus f dash x. Therefore, I equal to integral e power x tan minus 1x plus 1 by 1 plus x square dx equal to e power x tan minus 1x plus c.
Definite integral. A definite integral is denoted by integral a to b f of x dx, where a is called the lower limit of the integral and b is called the upper limit of the integral. The definite integral is introduced either as the limit of a sum or if it has an antiderivative f in the interval a, b. Then its value is the difference between the values of f at the end points, that is, f of b minus f of a.
Find integral 0 to 2 x square plus 1 into dx as the limit of a sum. Solution. By definition, integral a to b f of x dx is equal to b minus a into limit n tends to infinity of 1 by n into f of a plus f of a plus h up to f of a plus n minus 1 into h, where h is equal to b minus a by n. In this example, a is equal to 0, b is equal to 2, f of x is equal to x square plus 1 and h is equal to 2 minus 0 by n, which is equal to 2 by n. Therefore, integral 0 to 2 x square plus 1 into dx is equal to 2 into limit n tends to infinity of 1 by n into f of 0 plus f of 2 by n plus f of 4 by n up to f of 2 into n minus 1 by n is equal to 2 limit n tends to infinity of 1 by n into f of 2 square by n square plus 1 plus f of 4 square by n square plus 1 up to 2n minus 2 to the whole square by n square plus 1 is equal to 2 limit n tends to infinity of 1 by n into 1 plus 1 up to 1, which are n terms, plus 1 by n square into 2 square plus 4 square up to 2n minus 2 whole square is equal to 2 limit n tends to infinity of 1 by n into n plus 2 square by n square into 1 square plus 2 square up to n minus 1 whole square is equal to 2 limit n tends to infinity of 1 by n into n plus 4 by n square into n minus 1 into n into 2n minus 1 by 6 is equal to 2 limit n tends to infinity of 1 by n into n plus 2 by 3 into n minus 1 into 2n minus 1 by n is equal to 2 limit n tends to infinity into 1 plus 2 by 3 into 1 minus 1 by n into 2 minus 1 by n is equal to 2 into 1 plus 4 by 3 is equal to 14 by 3.
Area function. We have defined integral a to b f of x dx as the area of the region bounded by the curve y is equal to f of x, the coordinates x is equal to a and x is equal to b, and x-axis. Let x be a given point in a, b. Then integral a to x f of x dx represents the area of the shaded region in the figure. The area of this shaded region depends upon the value of x. In other words, the area of this shaded region is a function of x. We denote this function of x by a of x. We call the function a of x as area function and is given by a of x is equal to integral a to x f of x dx.
Integral 4 to 9 root x by 30 minus x power 3 by 2 whole square into dx. Solution. Let I is equal to integral 4 to 9 root x by 30 minus x power 3 by 2 whole square into dx. We first find the antiderivative of the integrand. Put 30 minus x power 3 by 2 is equal to t. Then minus 3 by 2 into root x dx is equal to dt, or root x dx is equal to minus 2 by 3 into dt. Thus, integral root x by 30 minus x power 3 by 2 whole square into dx is equal to minus 2 by 3 into integral dt by t square is equal to 2 by 3 into 1 by t is equal to 2 by 3 into 1 by 30 minus x power 3 by 2 is equal to f of x. Therefore, by the second fundamental theorem of calculus, we have I is equal to f of 9 minus f of 4 is equal to 2 by 3 into 1 by 30 minus x power 3 by 2, where the lower limit is 4 and the upper limit is 9, is equal to 1 by 3 into 1 by 30 minus 27 minus 1 by 30 minus 8 is equal to 2 by 3 into 1 by 3 minus 1 by 22 is equal to 19 by 99.
Evaluation of definite integrals by substitution. To evaluate integral a to b f of x dx by substitution, the steps could be as follows. 1. Consider the integral without limits and substitute. Y is equal to f of x or x is equal to g of y to reduce the constant of integration. 2. Integrate the new integrand with respect to the new variable without mentioning the constant of integration.
Evaluate integral 0 to 1 tan inverse x by 1 plus x square into dx. Solution. Let t is equal to tan inverse x. Then dt is equal to 1 by 1 plus x square into dx. The new limits are when x is equal to 0, t is equal to 0, and when x is equal to 1, t is equal to pi by 4. Thus, as x varies from 0 to 1, t varies from 0 to pi by 4. Therefore, integral 0 to 1 tan inverse x by 1 plus x square into dx is equal to integral 0 to pi by 4 t into dt into t square by 2, where the lower limit is 0 and the upper limit is pi by 4, is equal to 1 by 2 into pi square by 16 minus 0 is equal to pi square by 32. Evaluate integral 0 to pi x sin x by 1 plus cos square x into dx. Solution. Let I is equal to integral 0 to pi x sin x by 1 plus cos square x into dx. Then by P4 we have I is equal to integral 0 to pi minus x into sine of pi minus x into dx by 1 plus cos square of pi minus x is equal to integral 0 to pi minus x into sine x dx by 1 plus cos square x is equal to pi into integral 0 to pi sine x dx by 1 plus cos square x minus I, or 2i is equal to pi into integral 0 to pi sine x dx by 1 plus cos square x, or I is equal to pi by 2 into integral 0 to pi sine x dx by 1 plus cos square x. Put cos x is equal to t, so that minus sine x into dx is equal to dt. When x is equal to 0, t is equal to 1, and when x is equal to pi, t is equal to minus 1. Therefore, by P1, we get I is equal to minus pi by 2 into integral 1 to minus 1 dt by 1 plus t square is equal to minus pi by 2 into integral 1 to minus 1 dt by 1 plus t square is equal to pi into integral 0 to 1 dt by 1 plus t square by P7, since 1 by 1 plus t square is even function, is equal to pi into tan inverse t, where the lower limit is 0 and the upper limit is 1, is equal to pi into tan inverse 1 minus tan inverse 0 is equal to pi into pi by 4 minus 0 is equal to pi square by 4.
Example, evaluate integral 1 to minus 1 sin 5x cos 4x dx. Solution. Let I equal to integral 1 to minus 1 sin 5x cos 4x dx. Let f of x equal to sin 5x and cos 4x. Then f of minus x equal to sin 5 minus x cos 4 minus x equal to minus sin 5x cos 4x equal to minus f of x. That is, f is an odd function. Therefore, by P7, 2 I equal to 0.